I know. But now this feels full, you know? Yeah. Only if you're mad.
Okay, it's 101, so let's...
Hi everyone, my name is Edwin and I'm really happy to present our first presenter today, Chris Bonnet. Chris is originally from Bryn Mawr, Pennsylvania. He originally was a chemistry major and considered CS and classics before taking linear algebra with Shariari and falling in love with math. A fun fact about Chris, while at his REU at North Carolina this past summer, he met Clay Aiken, who is a American Idol runner-up 3 times. Next year, Chris hopes to go to math grad school, and when Chris isn't in Millikan, you can find Chris singing in the choir and in the Glee Club. With that, here's Chris.
Hi, everyone. Thank you, Edwin, for that wonderful introduction, and thank you all for coming out. It's so nice to have a full house for this. So today we're going to talk about the density of quotient sets generated by binary quadratic forms in the p-adics. Now that is a really, really, really long title with a lot of words, so we're going to break it up and kind of go piece by piece through all the different parts, and then in about the last 5 minutes we're going to synthesize it all and really talk about what the question of my thesis is. Now if you can hold on for the first 15 minutes, that's awesome. If you get confused in the last 5 minutes, I'm okay with that. So, let's start with a metaphor. We have the fraction factory, and the fraction factory does one thing. It makes fractions. And people come to the fraction factory and they say, I want you to approximate my favorite real number with a fraction. So a machine spits out the numerator, a. The numerator is a whole number. Another machine spits out the numerator, or the denominator, b, which is another whole number. And together they make the fraction a over b. So an engineer might walk through the door and say, I want pi to 1 digit. So the fraction factory says, okay, here's 3 over 1. A chemist might walk through the door and say, I want pi to 3 digits, because I'm just a little bit better than the engineer. So the fraction factory would say, here's 157 over 50, 3.14. And finally, a pastry chef might walk through the door and say, I want pi to 47 digits, because I go to Pomona. And so the fraction factory would spit out this monstrosity, which, if you'll trust me, is pi to 47 digits. So what are we really illustrating here? We're illustrating a concept called density. No matter how accurate someone wants their representation of pi, I can return a fraction that is that accurate. So more formally, we need a metric space, which is just a place where we can talk about distance. Then a set S is dense in X if for every non-empty open subset of X, there exists an element of our set living inside that non-empty open subset. Now that's also really confusing, so we're going to talk through some examples. First of all, the rational numbers are dense in the real numbers. We just saw that at the fraction factory, right? No matter how accurate someone wanted pi, I could return a rational number that was that close to it. The set of all possible fractions of 1, 2, 3, so 1, 2, 3, 1/2, 1/3, 2/3, and 3/2, is not dense in R because if you look at the interval 4 to 5, there's no fractions living inside that interval, so we're not dense in R. Another way to think about it is with this picture. So if I have an open ball on the number line from 0 to 1, there's a fraction that lives inside that ball. And then you might say, well, what if I made the ball smaller? Well, I would say, okay, there's still a fraction that lives inside that ball. And I could make the ball even smaller, and there would still be a fraction living inside the ball. So this matches our definition of density, where we said in any open subset, there has to be a fraction. So one day, the fraction factory is chugging along, and the machine breaks down. Instead of spitting out whole numbers, it starts spitting out whole numbers that are the sums of squares. And similarly, the denominator machine also only spits out the sums of squares. So now, instead of fractions a over b, we have fractions x squared plus y squared over z squared plus w squared. And so, what mathematical concept am I trying to illustrate here? I want to talk about quotient sets. So, formally, a quotient set is just all the possible fractions made out of a subset of the natural numbers. For example, if we let the subset of the natural numbers be the natural numbers, then making all possible fractions would give us the positive rational numbers, right? That's just exactly how we define the rational numbers, they're quotients of whole numbers. We only get positive numbers because the natural numbers are only positive. If we let a be 1, 2, 3, like we saw earlier, we get all the possible fractions 1, 2, 3, 1/2, 1/3, 2/3, and 3/2. And finally, now the fraction factory is giving us this quotient set. We have sums of squares, and we're making all of the possible fractions out of the sums of squares. So the logical question to ask is, can the fraction factory still do its job? Can we still approximate pi using these weird fractions that are now sums of squares instead of just whole numbers? And luckily for us, the answer is yes. The proof of which is long, complicated, and not really important to this, but suffice it to say, if someone wants pi, I can actually approximate pi using these weirder fractions. So now that we've talked about density, which was this idea that we could open up a ball and always find a fraction living in that ball, and we've talked about quotient sets, which are some kind of generalization of fractions, we can now talk about the world in which we're going to be doing this math, and it's called the p-adics. So we're going to take our metaphor one step too far. So one day, the fraction factory is chugging along, spitting out sums of squares, when the aliens from the movie Arrival land. Now, the fraction factory is really confused. What are these aliens doing on Earth? So they do the only thing they know how, and they call Amy Adams. And they say, Amy Adams, we need you to figure out what these aliens want. So Amy Adams goes on the ship, and Amy Adams says, what do you want? They say, we want you to approximate our numbers using your fraction factory. And Amy Adams goes, okay, well, what number system do you use? And they say they use the p-adics. So Amy Adams comes back to Earth and gives the fraction factory a lesson in the p-adic numbers. Now, as is often the case when aliens land on Earth, they end up teaching us the most about ourselves. So we're going to start with constructing the real numbers, which is a world we're all comfortable and familiar with. So to do that, we have to start with this definition of a Cauchy sequence. A Cauchy sequence is that, but what I really want you to think about is, as you walk along your sequence, the terms get really, really close together. They don't necessarily reach a limit, but they get closer and closer together. So a familiar sequence that's Cauchy is the sequence 1 over n. It's Cauchy and converges to 0 because as n goes to infinity, the terms get really, really, really close together. A sequence that's not Cauchy is this one. 5, 5 squared, 5 cubed, etc. That diverges to infinity, right? The terms are actually getting farther and farther apart as we walk along in the sequence. And then if we have this sequence, which is a rational approximation of pi, we find that it's Cauchy, but it's not converging to an element of the rational numbers, right? This sequence converges to pi, which is irrational. And so what have we done? We found out that there's a hole living inside the rational numbers, and holes are bad. So what we want to do is we want to patch this hole. We had a bunch of rational numbers that led us to an irrational number, and we want to include that number. So what we're going to do is we're going to create a new world and just say, in our new world, the real numbers is the set of limit points of Cauchy sequences with respect to the usual absolute value. So if we're walking along a sequence and we reach a number that wasn't rational, we just say, okay, now that number is a real number. So what we've done is constructed the real numbers, which is kind of a funky thing to think about because we use real numbers all the time, but real numbers, in fact, have to be mathematically constructed. So you'll notice I said the usual absolute value on Q. And that's because our definition of Cauchy sequence relied on having an absolute value in it. It said the absolute value of xm minus xn is less than epsilon. So the aliens say, we have a different absolute value function. And in fact, your absolute value function is just one kind of absolute value function. So the aliens say, by definition, an absolute value function just has to satisfy these three constraints. If you put in 0, you get out 0, the function's multiplicative, and the function follows this thing called the triangle inequality. So luckily for us on Earth, the absolute value function that we all know and love satisfies these axioms, right? If we put in 0, we get out 0. The absolute value of negative 2 times 3 is the same as the absolute value of negative 2 times the absolute value of 3. And if you trust me, it follows the triangle inequality. So the aliens introduce us to their absolute value function. So they say, okay, take an element of the rational numbers and fix your favorite prime p. Personally, my favorite prime is 659. So what you're going to do is you're going to factor out all the powers of p so that your fraction is no longer a over b, it's p to the k times a prime over b prime. And then we're going to define the p-adic absolute value to be this. So we factored out all the powers of p, and then we just take the reciprocal of it. So there are some things I want you to notice about this function right off the bat. The first thing is that it's discrete, right? In our usual sense of the absolute value, we can stick in a real number and get out a real number. But here, no matter what we stick in, the only thing we're going to get out is multiples of p. And the fact that the absolute value is discrete makes for some really weird and interesting properties in the p-adics. The other thing I want you to notice is that we have 1 over p to the k. So the more powers of p you have living inside of you, the smaller the p-adic absolute value actually gets. And likewise, if you have very few powers of p, the absolute value function gets bigger. And that's really counterintuitive to us, because we're used to, as elements get really, really big, they're really, really big. But here, when our elements are big, they're actually going to be very, very small. So let's do a few examples. The 47th adic absolute value of 47 is 1 over 47, because there's 1 power of 47 living inside 47. Similarly, for 47 to the 5th, we have 1 over 47 to the 5th, because there's 5 powers of 47 living inside 47 to the 5th. If we had 1 over 47 squared, which is a number that we would consider to be small, its absolute value is actually bigger because of the reciprocal. And then finally, if we had chosen the 3 adic absolute value instead of the 47 adic absolute value, we would have found that the 3 adic absolute value of 1 over 47 squared is 1, because there's no powers of 3 living inside 1 over 47 squared. So, by changing our absolute value function, new sequences will converge under that definition we had earlier. So let p equal 5, and remember that as elements of Q get bigger in our sense, they actually get smaller in the land of the p-adics. So our familiar sequence 1 over n is no longer Cauchy, and it actually diverges, which is really, really weird and confusing, because we saw earlier that it definitely went to 0, but now under this new absolute value, because the elements are getting really, really small, the absolute value gets really, really big, and we no longer converge. If we have the sequence 5, 5 squared, 5 cubed, that is Cauchy now, and it converges to 0. Because if we're using the 5 adic absolute value, as things get bigger and bigger and bigger, they actually get smaller. So this is just a brief glimpse into the weird world of the p-adic numbers, and the fact that sequences that we're familiar with in the real numbers end up behaving really, really, really differently in the p-adics. So just like we patched over the holes in the rational numbers using our old absolute value function, the aliens say that the p-adic numbers are the completion of Q with respect to the p-adic absolute value. We walk along our sequences, we find an element that wasn't in Q, and we say, we're going to patch the hole and call that the p-adic numbers. So, you might say, Chris, the p-adic numbers seem like they depend on the prime p. You said fix a prime p, and then you get the p-adic numbers. And that's correct. For every prime p, we get a unique p-adic space. And that's due to Ostrovsky's theorem. Ostrovsky's theorem also says that all of these p-adic spaces are different than the real numbers. And the coolest part about Ostrovsky's theorem is that it says these are the only possible completions of Q. So if any other alien civilizations landed on Earth and presented us with a really, 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 really weird absolute value function, we would actually know that it's equivalent either to our absolute value function or to one of the p-adic absolute value functions. And so this kind of motivates us to work in the world of the p-adics, because it's really the only other world other than the real numbers that we could work in. So the question now becomes, can the broken fraction factory that's spitting out sums of squares approximate numbers in the p-adics? And as the answer is often in math, sometimes. So, what do I mean by sometimes? Here we have a theorem, and it says if we have the quotient set of the sums of squares, so our broken fraction factory with square fractions, then it's going to be dense in the p-adics if and only if the prime you chose was congruent to 1 mod 4. Congruent to 1 mod 4 just means when you divide p by 4, you have remainder 1. And so this tells us exactly when and when we cannot approximate the aliens' numbers. If the aliens' p is congruent to 1 mod 4, we can do it. If it's not congruent to 1 mod 4, we can't do it. This theorem is due to Professor Garcia and some student researchers from Pomona a few years ago. And so what do we have? We have binary quadratic forms popping up. So what's a binary quadratic form? The function x squared plus y squared is a member of a bigger family of functions. And this bigger family of functions look like this. It looks like ax squared plus bxy plus cy squared, where a, b, c, x, and y are integers. And so as you can see, if we set b equal to 0 and a and c equal to 1, x squared plus y squared is a binary quadratic form. So to generalize the result we saw on the previous screen, we would want to know what happens if we made fractions out of the numbers that get spit out by binary quadratic forms in general. Is that set going to be dense in the p-adic numbers? Will the fraction factories still be able to help the aliens? And the answer, as it turns out, is sometimes. So here's a theorem that we were able to prove this semester. And it says, given a binary quadratic form and an odd prime, so a prime that's not 2, then if p doesn't divide b squared minus 4ac, the quotient set will be dense in the p-adics if and only if q is isotropic modulo p. Now that's a lot to take in at one moment, so let's break it down a little bit. We have a function, q of xy, it's spitting out whole numbers, and then we turn those whole numbers into fractions. We fix a prime, an odd prime, and then we say we want to make sure the prime doesn't divide b squared minus 4ac. It turns out b squared minus 4ac is called the discriminant of the quadratic form, and you can think about it like the last name of the quadratic form. So a bunch of quadratic forms find out the same discriminant, they have the same last name, they have similar properties, but they're not exactly the same. So if all of those things are satisfied, our fraction factory can help the aliens if and only if q is isotropic modulo p. And all that really means is that the function q spit out the prime p. So if the function q spits out the prime p, we can help the aliens. So what happens if p does divide b squared minus 4ac? This is a property known as singularity. We would say that the quadratic form is singular modulo p, and it's really, really bad. And most number theory textbooks kind of ignore the cases when p divides b squared minus 4ac. We had a really awesome proof of what happens. We conjectured that the quotient sets would never be dense, but unfortunately we had a loss of without loss of generality step that lost a lot of generality, and we were wrong. So we're working to patch that right now. And then the other question is what happens when p equals 2? 2 is the only even prime, and it in my opinion, kind of stinks. So we've been working to figure out what happens in that exceptional case where p equals 2. And we have some good results and some results that also relied on the same without loss of generality that is now wrong. So that's kind of where I'm going to be going for the rest of the semester, is trying to patch those holes. And so I want to thank Professor Garcia for being such an excellent research advisor and for exchanging over 230 emails with me in the past 6 months. I want to thank my friends and family for being here today, for watching on the live stream, and for listening to me talk about my thesis until they were sick of hearing about it. And I want to thank my research advisors from over the summer who really gave me the skill set I needed to do this thesis and are also helping me on some theorems that require a bit more intense algebraic number theory. So, thank you. Are there any questions?
What's your conjecture for the dynamic case?
For the case when p equals 2? So when 2 doesn't divide the discriminant, we actually get the same result back as when p was an odd prime. But when 2 divides the discriminant, I conjecture that we can actually get density in some cases, which is a bit weird because we would expect it to fail in all cases. But it really depends on the coefficients of the quadratic form modulo 8 of all cases.
So you said the only possible absolute value definitions that fit the enumerated properties of actual values are our definition or one of the p-adics?
Yeah.
Why is that true?
So it turns out that what you can show is that the different absolute values induce the same open sets, and then from there you kind of like that's our definition of equivalence, basically, that they make these like equivalent topological structures. And so if you can show that, you'd be able to show that any other absolute value function actually makes the same open sets as one of those. Yeah, so the more formal definition of isotropic is actually that you, if you represent something that's 0 modulo p, the inputs must have also been 0 modulo p. No, sorry, that's the definition of anisotropic. So if it's 0 modulo p, it must have been that the inputs were not 0 modulo p. But you can really just think about it as it spits out the number p.
So you said that the p-adics are in fact dependent on p, and those are all different spaces that are different from our usual understanding of So by that, do you mean like they're not homeomorphic, or?
I do not know. I would say the homeomorphic sounds right, but I haven't thought about the actual construction of the p-adics since the very first week of the semester.